Action logic is a family of formal logical systems designed to reason explicitly about agents, actions, and their outcomes. Unlike classical logic, which focuses on static truths, action logic is concerned with what agents do, what they can do, what they bring about, and how their actions shape the future. A central aim is to represent agency in a way that distinguishes between what merely happens and what is intentionally achieved by an agent. One of the most influential forms of action logic is seeing to it that logic, often abbreviated as STIT logic. Seeing to it that logics are designed to capture statements of the form agent A sees to it that F, which express that an agent actively ensures that a certain condition holds, rather than the condition holding accidentally or by natural necessity. Action logic thus occupies an important place at the intersection of logic, philosophy of action, ethics, and theoretical computer science. Classical logic and even standard modal logics are limited when it comes to representing agency. Classical logic can say that a certain outcome occurs, but it does not tell us whether it occurs because of an agent's action by chance or by external necessity. Similarly, ordinary modal notions such as possibility and necessity do not distinguish between what an agent can make happen and what may happen regardless of the agent's choices. Action logic was developed to address these and other shortcomings. Philosophically, it has been used to analyze concepts such as ability, omission, responsibility, control, obligation, and intention in a precise way. For example, moral responsibility often seems to depend on whether an agent could have done otherwise and whether the outcome was under the agent's control. In computer science and artificial intelligence, action logic is useful for modeling decision-making systems, multi-agent interaction, and planning. In legal and ethical theory, it helps clarify notions such as blame, obligation, permission, and prohibition by linking them directly to agents and their actions. The core idea of seeing to it that logic is to introduce a modal operator of the form A stit F. Agent A sees to it that F. Intuitively, this means that F holds as a result of agent A's choice or action. Sometimes a further condition is added that F would not necessarily have held if the agent had acted differently. Seeing to it that logics aim to formalize the distinction between agency and mere occurrence. Different variants of STIT logic exist, including achievement STIT, deliberative STIT, and historical STIT logic, each capturing different aspects of action and control. Despite their differences, they usually share a common semantic framework based on branching structures of time and possibility. The syntax of action logic typically builds on propositional logic. Formulas are constructed from propositional variables using standard logical connectives such as negation, conjunction, and disjunction. To this base language, action logics add modal operators indexed by agents. In seeing to it that logics for each agent A, there is a corresponding operator, A stit. Additional modal operators may include necessity, possibility, or temporal operators, depending on the system. The resulting language allows the expression of statements such as an agent sees to it that a condition holds. No matter what an agent does, a condition will hold. There exists an alternative action the agent could have taken, leading to a different outcome. The semantics of action logic, and especially seeing to it that logic, is usually given in terms of branching time or branching possible world models. These models represent time, or reality, not as a single linear sequence, but as a tree-like structure of moments, where each moment may branch into multiple possible future histories. At each moment, agents are associated with choice functions that determine how the future branches depending on their actions. An agent's choice corresponds to selecting a set of possible histories compatible with that choice. Let us consider one possible definition of the truth conditions for the STIT operator. A formula of the form A stit F is true at an index, an ordered pair consisting of a history and a moment on that history, if and only if F holds in all histories that result from the agent's current choice, while there exists at least one alternative choice the agent could have made leading to a different outcome. This captures the idea that the agent actively ensures F rather than F being inevitable. Logical consequence and validity in action logic are defined in a model-theoretic way, similar to modal logic. A formula is valid if and only if it is true at every relevant point in every action logical model. An argument is valid if and only if, in every model and at every point where all premises are true, the conclusion is also true. Because of the branching semantics, validity in action logic is sensitive to assumptions about agency, independence of agents, and the structure of time. These assumptions play a crucial role in determining which principles are valid in a given system. Several proof systems have been developed for action logic. These include axiomatic systems, sequent calculi, and tableau methods. Axiomatic systems typically extend modal logic axioms with principles governing agency and choice. Tableau and sequent-based systems are often used for automated reasoning and formal verification. In some cases, proof systems are tailored to specific seeing-to-it-that variants to reflect particular assumptions about time or agent independence. Action logic can be fruitfully combined with other logical systems. One important combination is with deontic logic, yielding systems that can express obligations and permissions tied to agents' actions, such as agent A ought to see to it that F. Action logic can also be combined with epistemic logic to reason about what agents know about their own actions and the actions of others, or with temporal logic to provide richer accounts of action over time, etc. Many standard action logical systems are sound and complete with respect to their intended semantics. However, properties such as decidability and complexity vary depending on the richness of the language and the assumptions built into the models. Branching time semantics and multi-agent interaction often increase expressive power, which can come at the cost of higher computational complexity or undecidability in stronger systems. Action logic, and seeing to it that logic in particular, provides a powerful formal framework for reasoning about agency, choice, freedom, responsibility, etc. By modeling actions within a branching structure of possibilities, these logics capture essential distinctions that are more or less invisible in classical and standard modal logic. As a result, action logic has become an important tool in philosophy, ethics, artificial intelligence, and formal theories of decision-making, offering a rigorous way to think about what agents do and what they bring about.